Okay, welcome back. All right, acids, bases, and salts, which are going to be applications of equilibrious systems. All right, so first of all, definition, what is an acid? Well, there's actually three different theories of acids and bases that we're going to go over. But if you're trying to recognize an acid on a test, for instance, by its formula, look for something that can donate H+. If it's got an H+ in there, it's going to act like an acid. For instance, carbonic acid dissociates into H+ and hydrogen carbonate. And if it's HCl, I said dissociate, I meant ionize. HCl dissociates into H+ and Cl-. The only one to be careful about is be careful with acetic acid, because we said in organic chemistry the carbon comes first. So the H+ is here at the end, and that will ionize and produce hydrogen plus the acetate ion. So an acid is something that produces H+, and an ionic material that produces H+. A base, well, actually, in all fairness, an acid can be a covalent molecule too. We're just going to say something that dissolves in water, produces H+. A base dissolves in water and causes the production of OH-. So, for instance, you could have something like sodium hydroxide dissociate into Na plus OH-. Or you could have ammonia, which reacts with water to produce ammonium and OH-. Again, as long as it produces OH- or has an OH- in the formula, we're going to treat it like a base at this level. A salt is any other ionic material which does not have an H+ or an OH-. So it can't have H+ in it, can't have OH-. So KCl, road salt, dissociates into K+ and Cl-. Again, it's ionic, breaks up into ions, but it is not an acid or a base. So there are thousands of different salts. And then the other thing would be a molecular substance, and maybe something like diatomic oxygen, something that's more covalent in nature. So they would give you a list of these things on a test and say, well, which one is the acid, or which group is our bases, salts, etc. And then this chapter is all about the KQ for how these acids and bases and salts behave in a water environment. All right, so let's go to some definitions, some stuff from middle school, although you say you learned absolutely no science in middle school. I know better. An acid, anything that produces H+ when it's dissolved, a base, OH- when it's dissolved. However, some properties of an acid, we know acids taste sour. You don't have to taste the battery. Trust us, it tastes sour. Things you have tasted, however, that taste sour would be something like a lemon or a lime, vinegar. And something that tastes bitter that's a base would be soap, if you ever got that in your mouth, or shampoo, among many other things. An acid reacts with metal to bubble out hydrogen gas. And both acids and bases are electrolytes, which means they produce ions. Now, they don't have to produce a lot of ions, but they produce some ions. And we'll write that in there, ions for electrolytes. Now, an indicator is a chemical that changes color based upon the acid concentration of the environment, what we call the pH of the environment. And you may have done something in middle school with what's called litmus paper. And there are two types of litmus paper, blue litmus and red version of the litmus. And in the presence of an acid, blue litmus turns into red, and in the presence of a base, red litmus paper will turn blue. There are many indicators, however. Litmus is just one of them. All right, definition of electrolyte to mesmerize. Now, can these things conduct electric current? Yes, they can. If you have free-moving ions in a water solution, they will conduct electricity, although they may not do it very well. And an indicator, like I said, changes color based upon how much acid you have in that environment. Now be careful with this. When we talk about pH, pH is a measurement of the environment. It is not a measurement of how strong an acid is or how strong a base is. It's just that environment, and we'll get into more of that on the video where we talk about pH. Other properties of acids, bases that we know from our work in the laboratory is that acids and bases will burn your eyes, nose, throat, and lungs. So substances you have to be careful with, even things that we eat, like jalapenos have a high acid concentration. In fact, a habanero pepper has a higher acid concentration, a lower pH, than a car battery. But yet we can eat those sort of things. I just wouldn't take a lemon and squirt it in my eyes, then of course it's going to burn my eyes and all that kind of stuff. Alright, 3 different theories of acids and bases. None of them are wrong. The first theory that came out about acids and bases is by a scientist by the name of Arrhenius. And Arrhenius said, hey, an acid is, and this is the definition we've been working on all throughout the course, is anything that when it dissolves in water produces H+, anything that dissolves in water produces OH-. Now, there are 2 other theories of acids and bases that developed after that, when they found things had the properties of acids and bases but didn't necessarily produce H+ or OH-. They developed other theories to go along with it. The Arrhenius theory isn't wrong. It's true that anything that produces H+ when dissolved in water is going to be an acid, and anything that's OH- is going to be a base, but they're not the only acids and bases that are out there. Second thing we got to be careful about, they're going to start talking about the KEQ for acids and bases, how much of these ions you produce. Do understand that dissolving doesn't necessarily mean produces ions. When we have dissolving, or what's called dissolution, you really have 2 things that are happening. First thing is called solvolysis, where the solute and the solvent interact with each other, and that causes particles to separate. And then a second thing, which is called Brownian motion, causes the particles to randomly mix, and that's based upon this random particle motion. So all types of dissolving, remember we did dissolving something ionic with water, and we said the water was polar, it had a positive end, so it pulled out the negative Cl- and salt, and the negative end of the water molecule pulled out the positive Na+ part, sodium chloride, and we said the water molecule has a job to do to dissolve it. That's only one type of dissolving. We also said like dissolves like. So polar dissolves polar materials and nonpolar dissolves nonpolar, and then we didn't do anything with how nonpolar dissolves nonpolar. Nonpolar undergoes solvolysis entropy, just like polar does. The only difference is with a polar material, you get a complete stoichiometric separating into ions. They call this dissociation. So ionic materials, most, not all, most ionic materials, let's say we have an ionic material AB, when you put it in water, we write a single arrow, and that breaks up into A+ plus B-. So the solvolysis of this causes a complete dissociation of the charge. In other words, you get 100% yield of the positive and negative ions. When you have something called ionization, that's solvolysis, that's dissolving also, but you get very few ions that are being produced in the process. For instance, let's say we had something like, go back to that. Say we had something like acetic acid. Now, that's covalent in nature. And so we don't normally think of ions, but we said that, look, there's really nothing that's purely 100% ionic and covalent. It's all governed by Coulomb's law. So you have some ions, Q1, Q2, and then you have the distance between the ions, which is more the covalent mechanism, which is the d² part. Everything has a little bit of both. So even something like acetic acid, which is covalent, will produce a small amount of H+ and acetate. And the K for this is 1.8 times 10 to the minus 5. So approximately out of 180,000 molecules of acetic acid, 1 will produce H+. But that's enough to burn your eyes, nose, throat, and lungs. So we would say that for instance, acetic acid is what we call a weak acid because we only get a small amount of ions in the process, and we call that process ionization, whereas with something that's ionic in nature, it tends to do what's called dissociation, where you get a 100% yield of ions, and we call that a strong electrolyte. So very few ions. We are dealing with the term weak electrolyte, and when you get stoichiometric yield of ions, we're going to call that a strong electrolyte. Okay, so to summarize, all of these things are dissolving. They all involve solvolysis. They all involve entropy. However, if it produces a small amount of ions, what you technically have is something called ionization, and we have a very small value for KEQ, like in that acetic acid example where it was only 1.8 times 10 to the minus 5. Whereas with dissociation, you're looking at a large KEQ. In fact, this KEQ is going to approach infinity. So we get a stoichiometric yield. All right, so what do they want you to do with this Arrhenius acid and base theory besides recognize, based upon the formula, which things are acid, bases, and salts? They want you to write dissociation and ionization equations. In other words, you're going to start with your material, your solute, and you're going to put it in a water environment, and then it's going to break up at least into some ions. Now, if it's a dissociation equation, we get a large amount of ions, so we use a single arrow. So that's the key here. Whereas if we have a covalent material, we're going to write an ionization equation where it's the same exact thing. I mean, take a look at the slides. There's dissociation, there's ionization, dissociation, ionization. The only difference is the fact that we're using double arrows for ionization, and our solute tends to be a covalent material, whereas with dissociation, we're using a single arrow, and this tends to be an ionic material. All right, so not much difference between the two. So what would it look like on a test? All right. Let's say something like, let's write the dissociation equation for, I don't know, let's do lead 2 nitrate. So they give you the formula, and they want a dissociation equation. So first thing you're going to do is say, well, is this ionic or covalent? Well, we have a metal, we have some non-metals, we have a polyatomic ion. This is ionic. So we're going to write a single arrow. Now, you don't have to write the water environment. We assume it's a water environment. You get lead and you get nitrate. Now, we have to go back to October. What's the charge on the nitrate group? It was one of the ones that I asked you to memorize. It is a single -1 charge there. And so that means since there's 2 nitrate groups in the formula, the total charge on the lead has to be +2. And then we just balance this out. 2 nitrate groups, and we put a plus sign there. There is my ionization equation. I'm sorry, dissociation equation. Or they may ask you to write, well, what is the ionization equation for ammonium? So we start out with NH4 plus for ammonium. And these are nonmetals, so we're going to write a double arrow, and we're going to break that up into H plus NH3. Here, try this one. Please write the dissociation equation for strontium hydroxide. I'll pause it and then come back to you. Hey, I'm back. All right, strontium hydroxide. Strontium's a metal. We got a group of nonmetals there, so we're looking at an ionic compound, so I'm going to use a single arrow. And I'm going to write strontium plus hydroxide. And strontium is in group 2 of the periodic table, so group 2 means +2 charge. And hydroxide means -1 charge, one of those groups I asked you to memorize. And there are 2 hydroxides. So, yes, the atoms balance on each side, but you also have to make sure the charges balance. There is a 0 charge on the left side with strontium hydroxide, but if you take the 2 plus and the 2 negatives and add them together on the right side, that also adds up to be 0. So not only do the atoms balance, but the charges balance as well. So we have to go back and we have to review what's the charge on all group 1 metals, +1. What's the charge on all group 2 metals, positive 2. And then we said for groups 3 through 12, it depends because they are transition metals and they have multiple oxidation states. We're not going to worry about group 13 except for aluminum, which has a 3+ charge. Group 14 does multiple oxidation states. So group 15 is going to be, when it's ionic, -3. Group 16, -2. Group 17, -1. And group 18, 0 charge. So you may have to go back to your notes on that and to go back and review those 8 polyatomic ions that I asked you to memorize. Okay. Bronsted-Lowry theory of acids and bases. Well, they found that not only do the materials that produce H+ act like acids, it turns out that anything that donates a proton is a Bronsted-Lowry acid. What is a proton? It's a hydrogen atom without the electron, which means an H+ particle. So let's go to our notes. Acids donate H+ during a reaction. Bases receive the H+ during a reaction. So if we compare reactants to products, the product that the acid becomes will have 1 less H+ in the formula, and the product that the base becomes will have 1 more H+ in the formula. And the product that the acid becomes we call a conjugate base. So acids become conjugate bases during the reaction, and bases become conjugate acids during a reaction. Okay. So a little bit of definition. In terms of conjugate acid, this is what they write in the book: the particle produced after the base accepts the proton. And I like that, but I told you it's a lot easier to remember if you take a look at the reverse reaction. If the material acts like an acid, but in the reverse reaction, as you go from products to reactants, that's your conjugate acid. And if it acts like a base during the reverse reaction, that's your conjugate base. So what do they want you to do on the test? They'll give you an equation, right, like this one, and they'll say, all right, identify the acid, identify the base, identify the conjugate acid, identify the conjugate base. Okay, we can do that. I did it color-coded because we say, well, if you start with HCl, what does it become? Well, although both HCl and water have hydrogen in their formula, HCl is the only thing that has chlorine in the formula. So HCl has to become Cl-. And water has hydrogen in the formula, but it also has oxygen. So it has to become the particle that has the oxygen in it. Okay. So how does that happen? Well, in the forward reaction, the hydrogen chloride, notice I didn't say hydrochloric acid because it's a gas, hydrogen chloride will donate its H+ to water. I'm going to draw an arrow there to show that donation of the H+ particle. So if you take H2O and you smack on an H+, you get H3O+. So water becomes H3O+. The HCl lost the H+ and becomes Cl-. If we look in the reverse reaction, in order for H3O+ to become H2O, it's got to lose an H+. So it's going to give its H+ to Cl-. So it's acting like an acid, but in the reverse reaction. So I would say that H3O+ is a conjugate acid. So if we were to identify things, we said that the HCl gets rid of H+, so it behaves like an acid. So the particle it becomes, I'm just going to write Cb for conjugate base, behaves like a conjugate base. It's going to act like a base in the reverse reaction. For every acid, we need a base. So if we identify hydrogen chloride as the acid, that means that water is going to behave like the base, which means it accepts the H+. So that means that the particle it becomes, I'm going to write Ca for conjugate acid, becomes the conjugate acid. It's going to act like an acid, but in the reverse reaction. So we would say hydrogen chloride and chloride are a conjugate acid-base pair. It doesn't really matter which one you write first, acid or base. They generally write the acid first, but look at the second example, water and hydronium. They don't. So it doesn't have to go acid first, then base. But we would also say that water, which becomes hydronium, also form a conjugate acid-base pair. So a couple of things that they might ask you to do on a test. They might say, oh, all right, we have this particle. What is the conjugate acid of HCO3-? Well, the conjugate acid is the particle it becomes after adding an H+. So we would say, all right, if we're going to make this a conjugate acid, then we're going to add H+ to it. So add H+. So that becomes H2CO3. If we have sulfate, what is the conjugate acid of sulfate? Again, you just add an H+ to it, and this becomes, oopsie poopsie, sorry, sulfate is SO4 2-. This becomes hydrogen sulfate, HSO4 negative. Now, some things can act like an acid under some conditions and act like a base under others. That term is amphoteric. If it is amphoteric, like hydrogen carbonate, we could say, all right, we have hydrogen carbonate. I want to know, what is the conjugate base of hydrogen carbonate? Well, to get the conjugate base, we have to remove an H+ from the formula. So if we get rid of an H+ from HCO3-, we wind up with carbonate, which is CO3 2-. So hydrogen carbonate can act like an acid under some conditions, and it can act like a base under others, and again, we call that substance amphoteric. All right, last thing I want you to do here for this section. Here's a reaction between, I'm not going to say what the thing is. If I say the name, it gives away whether it's an acid or a base. But let's identify in this reaction the acid, the base, conjugate base. You don't have to draw the arrow pushing diagram like I did. So I'm going to pause it. You identify those 4 things, and then we'll come back and go over it. Hey, I'm back. Pardon me. All right, so we take a look at the particle that has carbon and oxygen in it, and it becomes hydrogen carbonate. How did it do it? Gave away an H+. So we would say if it's giving away an H+, the H2CO3, the carbonic acid, that's why I didn't want to say the name, is going to act like an acid, and the particle it becomes is the conjugate base. Now, if we look at the reverse reaction, it's the ammonium that is giving away H+, so that it becomes ammonia in the reverse reaction. So we would say that NH4+ is acting like a conjugate acid, so therefore ammonia is the base. But we really don't have to do that. Once we've identified the acid, the other material is the base in the forward reaction. And then we look at the reverse reaction. Once we identify the conjugate base, the other material is the conjugate acid. Easy. Put a whole bunch of these on the test. You'll get 100. All right, now, one last thing I want to check here. That one, naming binary acids. I'm going to do this real quick just in case for my summer kids, if they're doing out of district and they ask you what a Lewis acid base is. Lewis acid base. A Lewis acid is an electron pair receiver, and a Lewis base is an electron pair donor. So here's an example. If you take boron trifluoride and you react it with ammonia, you get what's called ammonia borane, I think it's called. I forget what the systematic name is for it, the IUPAC name. But you get this reaction. If we take a look at the Lewis structures, boron can be stable without 8 electrons. It's an octet violator. So there's my Lewis structure for the boron trifluoride. Now, just because it's stable doesn't mean that it's not deficient. It is deficient. This is a pseudo-positive area here. It's deficient in charge, doesn't have 8 electrons around it. Whereas ammonia, the nitrogen has an unshared pair. We have our 3 hydrogens. And this unshared pair is highly electronegative. So the negative and the positive are attracted to each other. We say the ammonia donates the electron pair to the boron trifluoride, and that's what creates the bond. Now, that's one type of Lewis acid base reaction. There's a lot of different types of Lewis acid base. Right? Anyway, thank you very much, and we'll continue with nomenclature on the next program.